So, let us get started with Euler-Lagrange equation after having studied the Tikhonov functional and computing the differentials of this functional which separately over the standard error term and the regularization term, okay, and those are called the Frechet differentials. Now, given a linear differential operator capital D, we can find a uniquely determined adjoint operator denoted by d tilde for any pair of functions u x and v x acting on data points x. And this is subject to certain boundary conditions and assuming that they are sufficiently differentiable, that is up to a certain degree. Now, I look at this integral in an m dimensional space of u of x times this operator d times v of x dx, and this is the same as doing v of x and then an adjoint operator d tilde on u of x. Okay. Now, we make the following definitions. If I let u of x to be differential operator acting on f of x, some function of x, and v of x to be h of x, then this differential d E c of f comma h can be written in this form, right. It is integral over this m dimensional space. My h of x is like my v of x, and my d times f of x, the differential operator acting on f of x, is like my u of x per my definition, and I have an adjoint operator connecting v and u. Okay. And like what we saw earlier, this can be interpreted as an inner product between h and d tilde df in the space where the inner product is defined. Okay. Now, with the inclusion of a regularization term, I form my Frechet differential. So, what I bring in is I get in this this approximation error term, right, and I compute the inner product between h. So, I think the arrows here are sort of the other way around. So, this is my regulatory constraints, and my approximation error is with respect to the error between the desired response and the approximating function. Okay. Now, this Frechet differential is 0 for every h in this inner product space, provided this term, the second term, is set to 0. That means d tilde df, if it is equal to 1 upon lambda summation I equals 1 to n di minus f delta xi, then this Frechet differential is 0 for every h in this space. Now, what I do is I just simplify, I mean I want to bring in this delta xi indicating that I evaluate the function f at the point x equals xi, because this function f is a general hypersurface f of x and it can hold for all x in that space, but I am only sampling a set of data points from that surface which is f of x I, that is I am choosing x I and I know what f of x I is and that is my desired response d I, right. That is why, that is the reason why we need to bring in this delta x I. Okay. Now once I do the simplifications, it is straightforward. I get d tilde d times f lambda, because f depends on this lambda, is 1 upon lambda the summation I equals 1 to n of this deviation from the desired and the value of the approximating function at the data point xi times delta x minus xi, indicating that I evaluate at x equals xi. Now we bring in this notion of Green's functions and try to link these differentials appropriately. So we take a step aside and discuss something about Green's functions. So this equation A that I wrote earlier, right, which is d tilde d times f lambda equals this term here, it represents a partial differential equation in the approximating function capital F, whose solution is of interest to us. So towards this study, let us study let us understand what Green's functions are and how this can sort of fold in to what we are interested in, which is basically solution to this approximating function problem or this mapping problem. Let g of x comma zeta be a function of x and zeta. Zeta is some argument, so it could be a vector, it is a vector, and this function is called the Green's function and it satisfies certain properties. And the work on these Green's functions etc. was done by Courant and Hilbert. So given a linear differential operator L, g of x comma zeta satisfies the following properties. For a fixed value of zeta, g of x comma zeta is a function of x satisfying the boundary conditions. So you define the boundary conditions that are problem specific. There is some interesting property, except at x equals zeta, the derivatives of g of x comma zeta with respect to x are all continuous, and the number of derivatives is determined by this linear differential operator. So the linear differential operator L acting on this Green's function equals to 0 everywhere except at x equals zeta, where it is singular. Now L of G, L operating on G, is delta x minus zeta at x equals zeta. So when x equals zeta, it exists and it vanishes otherwise. And this function g of x comma zeta is called the Green's function of the linear differential operator L. Okay. and one can think about it as like the inverse of a matrix equation. So, if you have A times A inverse equals identity, it is something like that, right. The Green's, when you have a linear differential operator acting on the Green's function parameterized by x and zeta, this is delta x minus zeta. Now, let us see this in the context of our study here. Let phi of x be a continuous or a piecewise continuous function of x in an m dimensional space. Then f of x is given by this integral in the m dimensional space, the Green's function times phi of zeta, and this is a solution. This is a claim here. I think I want to make this clear. The claim is that this is a solution to L times f of x, L operating on f of x equals phi of x. So, let us verify the validity of this result and then see the connections to what we have. Now, I take L times f of x and I just plug in f of x here. So, f of x is this integral of the Green's function times phi of zeta over this m dimensional space, and I have L operating on this integral, and since it is a linear operator I can fold this L inside the integral. So, within the integral I have L times L operating on the Green's function times phi of zeta d zeta, but from the property of the Green's function, L acting on the Green's function gives me just delta x minus zeta. This is from the property of Green's functions. Now, this is a familiar integral. We have delta x minus zeta times phi of zeta, which exists when x equals zeta and 0 otherwise. So, this straightforwardly gives us phi of x, which is pretty nice because the linear differential operator acting on this function f of x, this is this approximating function, gives me just phi of x. Now, what is it in the context of our regularization problem? I can write my linear differential operator L to be d tilde times d, and I write my phi of zeta to be this equation here, which is 1 upon lambda summation over all the data points, the deviation between my desired and the approximating function evaluated at the data point xi. So, I plug this thing into my phi, right, because my f lambda is basically the integral of the Green's function times phi of zeta. I plug in this phi here and then I try to simplify this further. So, what I get is as follows, right. I just plug phi of zeta directly into f and I make my simplification. Right. So, here in this integral is over d zeta. So, I just pull this, I just put the terms that involve d zeta in the integral and I pull the other terms outside. So, in the integral I have this the Green's function g of x comma zeta times delta xi minus zeta d zeta, this integral, and outside I have pulled this term 1 over lambda times summation I equals 1 to n of this deviation di minus f of xi. but if you see carefully, this delta function exists at x at zeta equals xi. So, this whole integral collapses to g of x comma xi, because zeta has to be xi, otherwise this integral is at other points when zeta is not equal to xi, it vanishes. So, what we have simplified for our approximating function is f lambda as a function of this vector x is 1 upon lambda summation I equals 1 to n this deviation times Green's function g of x comma xi. So, x is a continuous variable because this is a surface, and xi are points, and you can interpret d suffix I minus f of xi upon lambda to be the weights that have to be provided to each of these Green's functions g of x comma xi that depend on the data point xi. So, I have n Green's functions here, right. I have totally n Green's functions corresponding to each data point xi, and I am scaling these, I am taking a linear combination of these Green's functions in this form. That is what this means. So, to sort of summarize just this equation that I wrote earlier, the minimizing function to the regularization problem is a linear superposition of n Green functions, and the points xi represent the centers of the expansion, and these coefficients d suffix I minus f of xi upon lambda, they represent the weights of this expansion, right. And you can think of these Green's functions centered at x equals xi, and you can interpret them to be the basis of a subspace of smooth functions where the solution to the regularization problem lies. Okay. Now, this is an important interpretation. That means I can get my f lambda, which is my surface as a function of vector x, using a linear combination of Green's functions. The weights associated with these individual Green's functions depend on my data pairs xi and di, and each Green function has a parameter that depends on the has an argument that depends upon the data point xi, right. This is a very important interpretation. Now, you may question how do I choose the weights, right. Now, w suffix I is 1 upon lambda of this deviation, that is di minus f of xi. So, if I set this definition, so I put a triangle here, this is how I define. Now, f lambda of x is basically a linear combination of Green's functions. I write it as summation I equals 1 to n w suffix I, this Green's function having these arguments x and xi. X is continuous and xi is a data point which is discrete. Now, I have n data points, I have n Green's function appropriately, and we evaluate this equation 1 at every point xj, j equals 1 to n, right. You just have to recall that this is a continuous variable So just to be clear, this is a continuous variable, but if I plug x vector to be x j, where x j are my sample points, I can link the left hand side and the right hand side of equation 1. Okay, so I do that, I evaluate at all these n data points I equals 1 to n. So let us define a few terminologies here. I would say these are matrix slash vector notations or terminologies. This f of lambda underscore is defined to be this vector f lambda of x1 so on till f lambda of xn. That is, I take this approximating function and I evaluate at the data points x1 through xn. That gives me an n dimensional vector, or this is basically an n by 1 column vector. Similarly, I have the corresponding desired response to be d1 through dn, and my weight is defined to be this vector w1 to wn, right. All the vectors are given with this underscore sign, and I define my capital G to be my Gram matrix that is formed by evaluating the Green's function over xi xj pairs, right, and this is an n by n matrix. So, I think with this definition, when I write it in matrix form, this vector w is 1 upon lambda d minus f lambda. It is straightforward. You take the scalar case, which is wi di and f lambda evaluated at xi, and I just use the matrix form of representation, and I land up with this equation w, which is 1 upon lambda d minus f of lambda, which means f lambda is basically d minus lambda times this vector w vector. But I know that f lambda is linked to w through this Green's through this Gram matrix G, right, which is whose each entry is evaluation of the Green's function at the data point xi xj, right. So, just to recall, G is your G xi xj evaluated at the point, and this is G is a matrix. So, f lambda is G times w. Now, I plug everything together, right. I want d, I just focus on this equation here, right. I want to get d on one side. So, it is basically f lambda plus lambda times w, but w vector can be written as identity times w, and that is what I do, and I just simplify my equation. So, G plus lambda I times this weight vector w is my desired response. And since L tilde equals L, that means the adjoint of the linear differential operator is the same. This implies that the Green's functions are symmetric, and this is what I have, right, and this matrix is symmetric. Now, all functions in the null space of D are invisible to the smoothing term or the regulatory constraints given by norm D operating on F. And this regulatory constraint is problem dependent. Okay. Now, let us see in the context of the RBF what is happening here. As a special case, we would like to choose some Green's functions to be translationally and rotationally invariant, and we can do that if we set this Green's function to be g acting on the norm of the vector x minus xi. In the context of the radial basis functions, so f lambda of x can be now expressed in this form. This is basically a linear combination of these Green's functions which have the special form, that is the g is basically g of norm of x minus xi, not a general g of x comma xi. And this is basically a linear function space, and it depends on the data, right. It is very important because these weights wi depend on xi and di. We assume Gaussian units in the radial basis function network, right. In the RBF network we use Gaussian units. So, this Green's function is written in this form: exponential minus 1 upon 2 times sigma I square times norm of x minus xi, where xi is the data point and sigma I is some spread parameter. And when we learned the hybrid learning algorithm, we said that we can partition the space into different clusters, and over each cluster I look at the cluster variance, right, and I can use that term here. And if I want to be avoiding too peaky or too flat distributions, I choose sigma square to be uniform for all the radial basis functions, function units, RBF units, and I can replace sigma I square in this equation to be sigma square, and that is the form that I have for my RBF response. Okay. Now, this idea will lead us. So, the idea that we have here using the Gaussian units and these weights, we saw that to be the case of the RBF network, but in general if I do not put the Gaussian unit and treat this as a Green's function, that will give rise to a general network comprising of Green's functions, and in the context of that we will look at this as Green's function based regulatory networks, learning networks. Okay. We will study that in this module.